Hello students, welcome to the class of teacher Meenal Pereira. In last video, we studied about the heating effect of electric current, and in today's video, we will be studying about the magnetic effect of electric current. Children, you have already studied about magnets and magnetic lines of force. Have you ever thought, is there any relation between electric current and magnetic field? Let's see all that in today's video. To study this, first we will consider a small experiment. As you can see in the diagram, children, we have connected a copper wire thicker and straight as compared to connecting wires between the points A and B. We have also kept a magnetic needle adjacent to the wire. We have kept the plug key open in the circuit and we have observed the direction of the needle. Now, as you all know that when the plug key is open, there is no current in the circuit. So, we will not observe any deflection of the magnetic needle. But once we close the plug key, and if we observe the direction of the needle, what we will notice? Okay, so here we will notice that as the current starts flowing, the needle is deflected from its position. So, because of closing of the plug key, the current will start flowing and the needle will show the deflection. So, this is the original position, south and north. This is the original position, and then we see that this dotted line shows the deflection. Okay, here also the dotted line shows the deflection. Now, interchange the connecting wires connected to the cell and observe the direction of the magnetic needle. What is the meaning of interchanging? Please look at the diagram. Initially, A was connected to positive terminal and B was connected to negative terminal. So, current was flowing from A to B. Now, see here, A is connected to negative terminal and B is connected to positive terminal. This is called as interchanging of connecting wires. And then, do you observe any difference? Of course. What is the difference? We find that the direction of magnetic needle is changed as we interchange the connecting wires. And how the direction is changed? When current flows from A to B, see here in the first case, A to B, the south pole of the magnet deflect towards east. Whereas when the current flows from B to A, the south pole of the magnet deflects towards west. Okay, so in the first case, it is deflecting towards east. In the second case, it is deflecting towards west. So, of course, there is a relation between the direction of the current and the position of the needle. So, what do we learn from this experiment? We learn that whenever current flows through a wire, magnetic field is produced around it. So, AB is a wire that is connected, and when current flows through this wire, magnetic field is produced around it. The magnetic effect is observed because of the current in the wire. So, that answers our questions that electricity and magnetism are closely related. On the contrary, if a magnet is moved and kept moving, we will observe the electric effect. So, electricity and magnetism are closely related. Now, let's see one more experiment. We will study about magnetic field produced around a conductor. Connect the circuit as shown in the figure. This is the connected circuit. When a large current, approximately 1 ampere or more, flows through a thick copper wire. This is the thick copper wire passing through a cardboard. This is a cardboard. The magnetic needle kept at different points on the cardboard around the wire stands in different direction. Now, this is the first place where the magnetic needle is kept. Okay, as we keep on changing the position, it will show the deflection in the different direction. The direction of the current shown in the circuit is its conventional direction. That means the direction in which the current flows. What changes are caused by increasing or decreasing current? What do you see when the magnetic needle is kept little away from the wire? Now let's see what changes. What do you think, children? When we increase the current, what will happen? And we decrease the current, what will happen? By increasing the current, the deflection of the needle also increases, and by decreasing the current, the deflection of the needle also decreases. Okay, and when the magnetic needle is kept away from the wire, its deflection is decreases. So that what we can say then, the deflection or the magnetic field depends upon how much current is flowing through the circuit. More the current, more the magnetic field. Lesser the current, lesser is the magnetic field. And as we keep the magnetic needle away from the wire, this is the wire, as we keep away from the wire, the deflection decreases. Okay, so now instead of magnetic needle, we will spread some iron filings on the cardboard and observe. These are some iron filings. Okay, so it is actually seen this way. The iron filings will arrange themselves in a circular manner. Very clearly you can see from both the diagrams that they have arranged in the circular manner. Why this happened, or what is the reason for this? As we all know that the magnetic field is produced due to electric current. And this magnetic field exerts a force on the iron filings, and that makes the iron filings arrange in a circular pattern. Okay, so the force that is exerted by a magnetic field forces the filings to take a specific position. So the iron filings spread along the magnetic lines of force. So this pattern what it has made, these are nothing but the magnetic lines of force. I hope it is clear to everyone. Okay, now we move further to right hand thumb rule. Okay, now what is this right hand thumb rule? Let's see. It is convenient rule for finding out the direction of magnetic field produced by a current flowing through an electric conductor. Okay, now imagine that you have held the conductor in your right hand in such a way that your thumb points in the direction of current. Now children, if you have pencil or pen, okay, just hold it, consider that as a current carrying conductor. Hold it in your right hand. Okay, now look at take your thumbs up, do thumbs up, see the position of the thumb, the direction, or the thumb shows the direction of the current. And now see your four fingers that you have curled, or with the help of which you have hold the conductor. Then these fingers shows the direction of the magnetic lines of force or magnetic field. Okay, so this is the right hand. This is the current carrying conductor. The thumb shows the direction of current, whereas the curled fingers shows the direction of magnetic field. Isn't it simple? Yes. Okay. Now let's study about magnetic field produced by current through a circular loop of conducting wires. In the previous experiment we saw one conducting wire. Now please look into the diagram. Here we have taken a loop. That means a round of wire we have taken. Okay, the wires are arranged in a loop. Then a very similar thing, as you can see here, this is a circuit. It is completed by connecting resistance, the ammeter, the cell, and a key, everything that is required for a circuit to complete. And then a cardboard here we can see, and then we can see a conductor loop. If current passes through the loop, the magnetic lines of force are produced at each point on the loop. Okay, so magnetic lines are produced at each point. Now here in the diagram only 2 points are shown to you, P and Q. But if you consider, the magnetic lines are produced through all or each point on the loop. And as we go away from the wire, the concentric circle representing the magnetic lines of force becomes bigger and bigger. This is as we are moving away from the wire. See the circles becoming bigger and bigger. As we go towards the center of the loop, the circle becomes so big that it's an arc that can be shown as a straight line. Okay, so this is suppose the center of the loop. So see, it is looking as an arc that is like a straight line. Okay, so as I told you in the diagram, it is shown at P and Q, but it is produced at every point. And by using or by making the use of right hand thumb rule, we can check that every point on the loop contributes the magnetic lines of force at the center of the loop, and these lines of force at the center of the loop are in the same direction. Okay, so as you can see that the magnetic lines of force that are produced are in the same direction. Please look at the arrow, children. Look at the direction of the arrow. We see that the arrows are moving now. See here, this direction, this direction. So it is moving in the same direction. So the intensity or strength of magnetic field at every point produced by a current flowing through a wire is dependent on the current. So this means that if there are n turns in the loop, the magnetic field n times of that produced by single loop will be created. So if we are using a single loop, then the intensity of the magnetic field will be less. And if we are using n turns of loop, that means n turns of wire, then the magnetic field will also increase n times. Okay, now we move to the magnetic field due to a current in a solenoid. Okay, now about solenoid, I think last year you have already studied. What is a solenoid? When a copper wire with a resistive coating is wound in a chain of loops like a spring, it is called as a solenoid. See in the diagram, this is the solenoid. Whenever an electric current passes through a solenoid, magnetic lines of force are produced in the pattern as shown in the figure. So these are the magnetic, this yellow color one wire is a solenoid, and what you can see here, these all are magnetic lines of force. Okay, so concentrated at the center, as we move away, it is taking a form of a circle. South and north pole of a magnet. The properties of magnetic field of solenoid are very similar to that of what is the magnetic field that is produced by a bar magnet. One of the open end of solenoid acts as a magnetic north pole and the other acts as a magnetic south pole. So one end acts as a south, one end acts as a north. The magnetic lines of force inside the solenoid are parallel to each other. See, this is the solenoid. Inside the solenoid, the lines are parallel to each other. What does that mean? It means that the intensity of the magnetic field within the solenoid is uniform everywhere. That is, the magnetic field in the solenoid is uniform. So inside the solenoid, the lines are parallel. This indicates that the intensity, that means the strength of magnetic field within the solenoid is uniform. That means same everywhere. And as you move out of the solenoid, you can see that it is forming arc. That means the intensity of the magnetic field is changing. Here it is more, as we move away, it is becoming lesser. Okay, so I hope it is clear to everyone what we studied today. It's an important part of the lesson. Please read it carefully. Thank you very much and God bless you.